So we'll be starting with the function requirements. So basically the usual pattern. So we'll start with the function requirements. Then okay. So since we are building LeetCode here, so there are mainly, I mean, the most basic functionality of LeetCode is that user sees a question and then user on the editor which is provided by the LeetCode, user writes code and then user submits the code, and then user I mean the platform basically provides the result of the submission. I mean, if it passed or not. So, so that is basically the most basic, I would say, functionality of LeetCode. And there is one more thing that happens in LeetCode, that is contests. So we won't be covering the contest part here, but we will. I mean, scale wise, we will basically consider for the peaks that happen, during the contests. But
Okay.
we won't really be talking about leaderboard and ranking and all those things. We'll just be, I mean, we'll keep it very simple. User will see a list of questions, so we can ignore the contest part. And
Mm.
if you just go to log in into LeetCode, you see a list of problems and you open a problem. You see the text of that problem, then you can choose a editor on the right side of any language, and then you put your code there, and then you submit, and then LeetCode basically gives you the result of the submission, whether it pass all the test cases or not. So
Mm.
that is the most I mean basic functionality that we will be talking about, and we'll be trying to build that. So function requirements basically come from the user perspective, so they are mostly written like, as a user I should be able to do this, those kind of things. So uh, first function requirement is basically user sees a list of questions. Then second would be user can see the description of the problem.
So I have a question here. A user can see a list of a problem. Then on clicking that one of the problem, he should be able to see the description, right?
Yes, yes.
Okay.
Yeah, that's what I meant actually. So when you see the list of questions, you click on one of them and then you are redirected to the problem statement.
Mm-hmm.
On the problem statement page, you basically see the description. So,
Okay.
or I actually better
You
to
see the entire
call it
problem.
problem statement of the problem. And then third is basically user can submit their code in their preferred language,
Mm-hmm.
and LeetCode provides the result of the summation.
But before that, there should be option to select the language as well, right? So that based on that, some default code used to appear.
Yeah, that
Like,
is, that's basically UI functionality. So when I say that user can submit the code in the preferred language, it means we need to provide the backend for any kind of language that user can choose.
okay,
But choosing is actually UI functionality. So yeah, we won't be talking about that.
okay, okay.
Then problem will have basically two things. One is the text, which is basically description, and the other thing is basically it has test cases.
Mm-hmm.
Now I think this will cover all the functional requirements. Have I missed anything here? No, I think this should be good enough.
Compilation thing is not there.
Sorry.
compilation thing. Like, and he won't be directly submitting the problem, right? So before that compilation,
No,
then the
that covers. I mean, in this part only. So when user submits the code, that code basically goes to lead code's backend. It gets compiled there, and then if there is a compilation error, but it's basically lead code provides the compilation error to the user. If there was no compilation error, then it goes for uh, running the code.
but in real time lead code, we see we have a option of run and submit. So if we run, then it's for our use only, and if we submit, then it goes to for other stuff. Like,
No, I think that also, I mean, doesn't work on local actually. So that still goes to local. I sorry, server, but it's like the question. I mean, the problem is, I mean, the text is actually, sorry, code is evaluated only on three of our provided test cases, but the code actually still goes to backend. So code is not really executed on the front end.
processing are different. We will be having different API for submit and run, or the API will be same.
It will be same actually. You just submit the your code and you get the result.
Okay, okay. Let's move ahead then.
Okay. So now let's talk about the non-function requirements. So in non-function requirements, we mostly talk about scale and the other properties of the system. So I mean, we actually talk from the perspective of system here only. So from systems perspective, the system should be able to scale, the online judge or lead code to this particular scale, and then system. I mean, the judge should stay available. Those kind of things. So in non-functional, first thing is basically it should be available all the time. Then uh, if we talk about consistency, so I mean, it's I would say so. I mean, it's difficult to apply cap theorem on the whole system. I would say, but yeah, cap theorem can actually be applied on the parts of the system. So, in terms of consistency, what I can think is if user is able to see some of this submission and maybe after 1 second if they reload, then they see the submission disappearing, that is still okay actually. So if I had to choose between availability and consistency, I think in this case we should choose availability.
Okay,
So
okay.
little
Next.
bit of state data is actually okay.
Mm-hmm.
So I'll just say eventual consistency. uh, I mean, partition tolerance we haven't talked about. So partition tolerance is basically whenever in any kind of system I mean, partition tolerance is I mean, it's given actually, so that has to be there, and we have to just choose between consistency and availability, because partitions do happen, and I mean, they'll happen anyway. So I mean, your system, when it's tolerating the partition, what should it choose? So yeah, so yeah, we will go ahead with availability when there is a partition. Now, one more thing that we haven't talked about is I mean, how many languages it should support. So we can assume, let's say it will support 20 languages. Then what should be the latency of submission of code? So let's say if I submit my code now, how long should I wait till I get the result? So if you have seen some old platforms, for example Spods, they actually take a lot more time than, let's say, LeetCode or maybe HackerRank. So these new age online juices are actually faster in terms of, or in terms of latency of the submission than the older ones. So I mean, so we will be sort of have a different kind of system when we are building that old age kind of system. So in this case, actually, we can assume that user should get the response within 5 seconds. So end-to-end latency of submission should be less than 5 seconds. Now, how much should be the scale? So LeetCode, last time I checked, it had, I think, 1,000 problems. So I mean, we can go, maybe if we can if we want to multiply it by 2 or 5, then I mean, at max it will have not more than 5,000 problems. So 5,000 problems. Uh,
If you say 5,000 problem, that means entire problems which are there on lead code is around 5K.
yeah, yeah. It's actually a lot less than that. Approximately 1,000 only.
Hmm. But there are like as per companies as well, right? So for that only, sometime it goes to more than 1,000 for some companies.
Yeah, I mean, still, I think it won't have more than 5,000 or 10,000. So
Okay.
it won't be in millions or billions. So it will still be in thousands only. So that's why I assumed 5,000 problems.
Yeah, yeah.
And 5,000 problems, let's say, for each problem the text takes, so text is usually, I think it can go up to 4,000 characters max. So 4,000 is basically, I mean, 4,000 characters is basically byte. So yeah, 4 KB description, 4 KB description, and then I'm assuming. So I've seen uh, how many test cases? I think I have seen up to 600 test cases for some problems. It's not 600, but definitely I've seen 100 test cases. So yeah, I think we can assume that we'll have 100 test cases per problem. 100 test cases per problem, and each test will have, let's say, some test cases can be quite large, but on average I think we can assume we will have 2 KB per test case. Although some test case would be much smaller. I mean, they would be in, let's say, 100 bytes or something, or even less than that. But yeah, there could be some you know extreme test cases which can go up to, I think, 10 KB as well. So yeah, that's why on average I think we can take 2 KB per test case. Now let's assume that in each contest, no yeah, I mean, we should first talk about the regular users. So regular users, let's say we have 1 million users of LeetCode. Yeah, but still, yeah, let's take up to 10 million, 10 million users. uh, I mean, daily active users would be, it's definitely not 10 million, but yeah, still, let's, you know for the purpose of scale, let's try to scale up to this number. So 10 million users, I mean daily active users, then we can assume that on average one user submits two problems, or let's say uh, yeah, I mean let's two problems I think would be sufficient to assume, but yeah, it can go up to 10 or maybe even I mean it could be any number, but yeah, let's assume five problems per user or five submissions. Submissions could be actually a lot more than that, so let's assume 10 submissions per user per day.
And
So
no, no, no. So 100 million users, daily active users we have, right?
hmm,
So per day, how many users you are considering?
per day I'm assuming
Per day,
10
one
million.
user is solving how many problems?
So problem is actually not of importance here. More important thing is actually submissions. So I
So
mean
submission can be more, right? Some people, if they are not able to solve, they submit multiple times.
yeah, yeah, yeah.
So
Yeah, I
10,
assumed
I
that
think
10
10.
on average, but yeah, it can, I mean, it will obviously fluctuate. So for some people, it will be a lot less than 10, but for others, it would be more than that.
Can we consider 100?
Okay. So 10 million users, daily active users, and 100 submissions per user. So this totals comes around 1 billion submissions per day. So if we, how much would be the, I would say number of submissions per second. So number of submissions per second would be, um, yeah, this is 1000, and we have actually 100,000. So actually 10 billion is basically 10 to the power 9, and then we have 100,000 seconds in one day, which is basically 10 to the power 5. So this comes around uh, approximately, yeah, 10,000 submissions per second.
Okay, okay.
But the thing is, for every submission, we are assuming, I mean, so we can assume that on average, one submission basically takes, I would say, 3 seconds. 3 seconds, 3 seconds for execution. It can go up to even more than that. Yeah, let's say on average, every submission takes 5 seconds to execute. And if we go ahead with polling, I mean, if we poll every second to get the result, then I mean there will be 5 times extra traffic. So the polling traffic to get the submission result, this can go up to 50,000
Okay.
per second. Okay. Now we had earlier said that we would be considering the contests as well. So there can be spiky traffic during the contests, and since there can be spiky traffic, yeah. So what happens is when a contest is running, uh, I mean, in the mid of the contest, you won't really see that much of submissions, but when the contest is about to end, you will actually see too many submissions. I mean, a lot of. I mean, basically the frequency of submission actually increases. So I mean, people just try to kind of try their last attempt. So at the end of contest usually the traffic is higher, so we can assume that it can go up to 5 times of usual traffic. So the peak submission traffic would be, yeah, that will be basically 50,000 per second.
Okay.
Okay, so I think we have talked about functional as well as non-functional. So now let's talk about what are the entities involved in this whole system. So if you list down the entities involved in your system before building the high level design, or going further, it actually helps you in creating the high level design very quickly. So, and it also kind of gives you the DB schema immediately. So that's why, I mean, I actually, at least write the entities beforehand. So the first entity is problem. So a problem will have problem ID, which could be an integer. Then it will have so the problem has description, and it has test cases, and it will have other metadata like total number of submissions, what is the um, what is the accuracy, those kind of things, when was it created, those so so the thing is, description can be quite large. I mean, it's 4 KB, so 4 KB can technically come, in most of the databases. 4 KB is not really a lot of data, but if we want to expand it, then it's so rather than putting the description in the database, we can actually store the description in a file, and put that in S3 or any blob store, and from there we can fetch it.
Yeah, yeah,
So same is, I mean, same thing goes for the test cases as well. So if you have basically actually seen the test cases, or if you have tried to set a problem in any of the contest, then you would have seen that test cases are nothing, they are actually files. So let's say if you are creating 5 test cases, then there will be 5 files. I mean, it doesn't, they don't really have to be separate files. You can just put all the test cases in a single file, but yeah, ultimately it's a file only. So yeah, so I'm assuming that we are putting all the test cases in a single file, and yeah, so that file can grow very large. So I mean, it will still be less than MBs, or definitely less than 10 MB. So yeah, it won't be that large. So yeah, but still it's a good idea to basically, the point is, it's good idea to put this in the blog store. So what we are going to do is, we will put text as well as test cases in S3, and here what we would be doing is, we would be storing their ID, the S3 URLs. So description S3 URL, which will be string, and then test case S3 URL, and then we'll have other things like number of submissions, etc., created at, and all those. So second entity would be, now we have got the problem part. The other thing is basically submission. So user makes a submission, so it will have submission ID, it will have problem ID to which we are making a submission. It will have language, then it will have code, so submission should have code. So code, I know that code cannot grow very large, so code we should be able to store in the DB cell itself. Although if we want to extend this functionality to keep huge code, then we can just again we can migrate this code to S3 and then just keep the URL here. But for now we will just keep the code here only. So code text, so we have submission ID, problem ID, language, code text, and maybe result. So result would be uh, I mean it could be anything, compiler or something like that, basically an enum. And of result also usually have details, so result details as well. uh, so we have problem, we have submission. Yeah, I think so. Of course, we can have the user and all as well. Actually, we should have user ID as well here.
And we have different user table, so which will contain details related to user ID, how many submissions he has done, like all those details.
No, that part will. I mean, the submissions, user submission data will be in the submission table.
Mm-hmm.
User table will contain only user information.
Okay,
So we actually don't need that here. That's why I skipped.
okay, okay.
So we have covered till here. Now let's talk about the APIs involved in the system. REST APIs. First thing is, so I'm sure there is some portal where you can add the problems and all, but from a normal user's perspective, we are the user only sees the problem, reads the problem. User doesn't really create the problem. So, but yeah, if we want to consider adding the problem to the system as well, then we can yeah, let's go ahead with that as well. So our first API is basically we want to see a particular problem, or maybe we want to see all the problems. So user should be able to the function, first function requirement was user sees a list of questions. So basically we should have I mean this API should provide the list of questions. So we will have slash problems. So problems basically so we will be following the REST model here, and problems becomes the resource here. So slash problems slash. So some people actually write all here, and some people don't write anything here. So I just won't write anything here. So I'll just add the query params here, whatever uh, you know we want to provide. So slash problems will basically provide us all the problems, the list of problems. But of course you're not going to see 1,000 or 5,000 problems on the same page. So it will definitely have some filters. So you can provide all those filters in query parameter here. For example, sorted by.
Can we do pagination here?
Yes, I was about to come to that. So sorted by maybe let's say difficulty. So this will, and sort order, for example, equals to descending. Then page. So page, let's say is 1. We are on the second page. And then page size equals to, let's say, Okay, so listing all the problems will look something like this. Then of course this is actually a get endpoint, so I forgot to write the method here. Second thing is basically, let's say if we want to provide the functionality of adding a problem. So adding a problem is basically, you are creating a problem. So that will be, you will make a post call to the problems endpoint, and here in the body you will provide things like text or test cases or those kind of things. So I'm skipping that part here. I mean the body, whatever that will go in the body. So now the third is basically we want to see the problem description of a particular problem. So for that we'll have get problems slash whatever is the problem ID. So if it was 123, then it will look like 123. So yeah, so this will basically provide all the details of a problem, and of course we won't be providing the test cases in this endpoint, but yeah. Now now let's talk about the submission. So for submission, what we are basically doing is we are basically when user submits their code, they are actually making a submission, so they are creating one submission. So if we take submissions as a resource here, so submitting the code will look something like this: post slash submissions, slash. So in the body basically user will provide all the other things like code and all, and if user wants to see the result of a particular submission, then they can just do get slash submissions slash submission ID. So this will be mostly the API part. I think this will cover all the APIs. Now let's talk about the high level design. So we have one user who is submitting their code, who is basically using LeetCode. So first thing is user comes to LeetCode, and user sees the list of problems, sees the description, and then it submits. So first thing is basically user has to see the list of problems or the problem description. So for that we will have, let's call it problem service or problem CRUD service. It's not we're not really providing the creation endpoint here, so let's just call it problem front end. The terminology could be anything, so let me just call it problem front end service. And this problem front end service will be backed by problem database. Let me just create the arrows. And when user basically user has to see the list of problems. At that time the request will go to the problem front end service. Problem front end service will just make a call to problem database, and it will fetch the list of problems based on the queries, and it will just return the result. Now user clicks on one particular problem and has to see the description. That request will also go to the problem front end service. This time it will get the data from the problem database, but it also has to get the text description. Description as just description actually, which is basically not stored in the problem database. So it's actually, since we discussed earlier, it was in S3. So here we have S3. So we have S3 here, and okay, so problem frontend service fetches the text from S3, and then it basically shows to the user. Now now user is on the problem page. User selects a particular language, and then user submits their code. So for that, we, let's say, have submission frontend service. So when user is submitting their code, the request comes to submission frontend service, and submission frontend service has to, first thing that it will do is basically it will create an entry in the submission database. Second thing is it actually has to run the submission, evaluate the code. So where do we evaluate the code? So if you have if you have seen basically your microservices, you must have seen that they are in one language only. So but the thing here is we have several languages. There can be up to 20 languages here. So what do we do in that case? One option is that we can have many different services which are, basically, we have many different services which are running in that particular language. So for example, we have two, let's say if we had just two languages, C++ and Java, then there would have been two services, one for C++ and one for Java. So that is one approach. Now the problem with this approach is the number of users are not really equally distributed among the languages. Some languages are too really popular. For example, Java is quite popular, and then other languages might not be that popular. For example, Haskell, or maybe other language, I'm not sure. So the problem with this approach is that it will eventually lead to unequal uses of resources. So some resources will be wasted for. So I'll give you an example. For example, let's say we have one language, and for that language we keep one service which is in that language. But the problem is, let's say only one request comes to that for that language per day. So all the time basically that service will just be sitting idle. It won't be doing anything. And since we also need to provide provide the availability, so for that we basically need to have one more server as the backup. So there will be two servers who would be just sitting there idle most of the time. So this approach will not lead to wastage of resources. So that's why we need to think of something else. So this was one approach. Maybe I can write, I can just draw these. Yeah, so this is basically Java service, this is C++ service, and this I'm calling approach 1. And let me also write down the problem with this. Cons unequal distribution of load, hence wastage of resources. Now the second approach is basically what we can do is, so you must have seen the virtual machines. So virtual machines are they are a kind of software using which what you can do is you can, let's say I am on a MacBook right now, and I need to do something on Windows. So if we didn't have any virtual machines, then what would I would do is basically I'll buy a Windows laptop, or yeah, a Windows laptop, or maybe I'll have to install Windows on a Linux laptop. So I'll need a separate machine basically. What virtual machine does it does is basically it kind of provides you virtual, I would say, environment in your computer. In that environment you can actually install uh, the operating system. So I can basically use a virtual machine in my computer, and I can, in that virtual machine, I can install Windows or Linux. And I don't really need any hardware for that. So that is the benefit of virtual machines. So they're basically nothing, they're just softwares. So if we actually use virtual machines, so the benefit of using virtual machine is we can have, I mean, single kind of service servers, and on each server we will have multiple virtual machines. So we can also distribute these virtual machines, I mean, on different servers. Just for example, let's say on server 1 we have Java plus C plus plus virtual machine, or on server 2 we have, let's say, Python and PHP virtual machines. So that could be one approach, or the other approach is basically we can just have all the virtual machines on a sing. I don't think that will be possible. Having all the like 20 virtual machines running on a single computer. So I don't think that will be possible. But yeah, using virtual machine is basically the idea here. So virtual machine is a good approach. So the benefit here is we can adjust our servers in a way that the load is equally distributed, and the resource wastage is minimal. So let's say uh,
Basically, here you are talking about servers, right? So we
uh,
could have server for more servers, since Java service is is being used more. So we will be having this service deployed in multiple servers, and their
yeah.
number will be more rather than the C++ services.
Hmm.
So yeah, I got it. Can we move ahead?
Okay. So approach to is basically use virtual machines. Now the problem with virtual machines is that they actually, I mean, slow down your system. They actually consume a lot of resources, and so they, I mean, they run on the application level. So I would say they consume a lot more resources, and we have kind of a newer technology called containers. For example, Docker. So they are much more lightweight in comparison to virtual machines. So Docker using containers is the third approach. So for example, Docker. So Docker, I mean, the containers give you all the benefits of virtual machines, but they are much more lightweight. So they consume much less resources. So resources, I mean, by resources I mean, CPU, RAM, disk, these three things. So the problem with virtual machines is that they need a full-fledged operating system to operate. So when you are installing a virtual machine, you have to, in that virtual machine you first need to install an operating system. In that operating system you will do your
So
thing.
as a whole, you mean to say that in our in case when we choose the virtual machine option, then we have to manually do everything. While in case of Docker, we have most of the thing inbuilt. It just we need to deploy our code.
No, we're not doing anything manually here. So virtual machines are actually, they're heavy in terms of the resources they need. So why they are heavy? Because they actually operate a full-fledged operating system in your system. I mean, first there will be virtual machine installed, so that is software. Inside that there will be operating systems install. So operating system usually consumes a lot of resources. It needs a lot of RAM and disk as well as CPU. So within that operating system, you will be running your code evaluation software. So but the thing with containers is that they don't install a full-fledged operating system. So whatever operating system you are using, they will their code is actually written in such a way. I mean, they that code is actually written uh, on that operating system only. So there will be you know uh, yeah, I mean, there will be separate installation files for, let's say, if you want to install Docker for Windows, or if you want to install Docker for Mac. So they don't need I mean, they don't install a full-fledged operating system. So you can actually uh, so that's why basically they are much more lightweight. So they are newer technology, they are much more lightweight. So using container, that's why is a better approach. So approach 3 is basically preferred approach. So what we are going to do here is we have, let's say, this server. Let's call it evaluation server. And this evaluation server has multiple containers for different languages. So let's say it has one Java container, and then it will have a C++ container like this. So so submission frontend service. First step is basically it will put an entry in the submission database. I mean, to create a submission, and then it will send that submission to the evaluation service. Evaluation service once done, then it will have to update the status somewhere. So of course it will update the status once done in the submission database only. And okay, now how does the user know? So I mean, yeah, so user will basically query the submission frontend service to check the status, and then it will get from the submission database. So one thing is basically, so let me take a note of the things we will be discussing so that I don't miss. To discuss, one is how user gets the result. Second, scaling the whole system. Third thing is basically failures or fault tolerance. Okay, so we'll be discussing three things. One is how will user get the result. So user made a user submitted their code in the submission frontend service. Submission frontend service cannot provide the response immediately in the same call, because it will take 5 seconds. We have already discussed that. So how will user get the result? So one approach is that user continuously posts the submission frontend service. So user sends a request to the submission frontend service, give me the result of my submission, and submission frontend service goes to the submission database, checks if if it's evaluated already or not. If not, then it will just return the response that it's still in evaluation. If it's evaluated already, then it will just say it will provide the evaluation response. So in one sense, basically user is basically continuously polling the submission frontend service. So polling frequency could be anything. It could be I mean, since we have assumed that one submission takes 5 seconds, so we can keep the polling frequency of 1 second here. So at every 1 second we will be basically polling the submission frontend service to get the result. That is one approach. So the second approach is basically you can basically compare it with other kind of problems where you need the status of something that is already happening on the back end. So you can use WebSockets or server-side events. But the problem with WebSockets and server-side events is that they're persistent connections. So we need to, let's say this is my, uh, these are my servers which are connected to the user. So user is maintaining their connection with these servers. So these servers, so now let's say if I want to make a deployment, then what do we do in that case? So we will have to kill all the traffic on this particular server. So it's not the normal kind of traffic, request response traffic, where the next request will go to the other servers when this server is down. We will have to drain these connections from here. So by draining, what I mean is basically we will have to wait for the users to leave that server. So I mean we won't be accepting any newer connections, and we will be waiting for the old connections to end. And once we don't have any connection on a particular server, then we can take that server and for the deployment. So WebSockets and servers and events, they are difficult to implement technologies. So unless really needed, nobody actually I mean for simpler things, actually nobody uses these technologies. So in this case, it's better to just go with the polling. So that's why we will just go with the polling here. uh, so we have talked about how user gets the result. Now second thing is basically scale. So let's try to scale it. So we have seen that the polling traffic can yeah, actually we didn't talk about the db technologies that we would be using. So yeah, let's have a look at the scale first. So you can actually see that we have 10,000 submissions per second, which means um, some 10,000 writes to this submission database. So 10,000 writes to the submission database. And we can also see that we are getting 1 billion submissions per day, which basically means 30 billion submissions per month. Yeah, and per year it would be 365 billion submissions per year. So feels like we won't be able to use a relational database here. One reason is that the amount of Sage data is really large. I mean the number of submissions here, and the other thing is basically the write traffic here, which is 10,000. So 10,000, I would say, if it's lightweight, the relation databases will be able to handle, but it's still like stretching the relational database. So it's better to basically go with a non-relational database here, or NoSQL database. So we need a NoSQL database which can handle huge amount of writes. Now let's look at the reads. When are the reads happening? So reads are happening within few seconds only. So until the you know that code is evaluated, only till then the reads are happening to the submission database. So user is polling to the submission front end service what happened to my submission, and then the submission front end service makes a call to the submission database to get the result. So the submission will be happening. I mean the reads. So read to write ratio, I mean I would say, is almost similar here, because uh, I mean the reads as well as write, I mean they happen kind of. So yeah, I mean in total there will be two writes to the to for a particular row. One is when we are creating that row, and the other is when we are updating the status of that row from the evaluation server. And the reads also will be 2 to 3 only for a particular submission. So read to write ratio is actually equivalent here. So we need a database that can basically handle huge traffic of writes as well as reads. So Cassandra will be a good choice here. So what we can do is we can use Cassandra for database. And since we are using Cassandra, so if we want to scale it, then we need to basically decide the partition key as well as sort key. So what will be the partition key? So we have so let's first look at the schema of submission. So submission has submission ID, it has user ID, and then problem ID, and then language, code, text, result. So if you have used LeetCode, then you would have seen that you know fetching the submissions of a particular user is actually is basically the kind of query that happens more frequently, rather than maybe fetching this all the submissions for a particular problem. Or yeah, so if we, let's say, go ahead with submission ID as a partition key, then that would mean the submissions for a particular user ID, the submissions would be kind of uh, scattered over all the shards. So but if we, let's say, choose user ID as a partition key, then that would ensure that all the submissions for a particular user, they lie on the same shard. So that's why we can go ahead with user ID as a partition key. Now for a particular user, what we when we are in that shard, so we usually see the submissions in the uh, in a reverse chronological order. So we want to see the recent submissions first, and then in that way. So the timestamp could be the sort key here. And yeah, I think that will work. But we using primary partition key and sort key, we kind of build a primary key. So one more sort key that we can use here is submission ID then. So combining these three will be a primary. So I'm not really sure how it works, but yeah, I think yeah, you can basically research. So Cassandra will be our database here. For problem, the read is actually a lot higher than the writes. The writes happen very rarely, I would say, in the problem database, but the reads are the ones which happen quite a lot. Now problems are problem database is sort of static database. If you want to how much would be the read QPS, so for the to the problem database, for reading the problem. So since we have 10 million users, so 10 million users, I'm assuming they would be seeing the problem list maybe 5 or 10 times a day, and they go to a problem, and then basically that problem is loaded once. So I think we can assume that there will be 50 million read calls to the problem database per day, or let's take let's say maybe 100 millions. Yeah, let's assume that one user is making 10 read calls. So 100 million reads per day for problems or problem database, so which comes around to 100 million is basically okay, 100 million reads per day is basically this would be 10 to the power 8 divided by 10 to the power 5, which is basically um, yeah, 1k reads per second. So read QPSC is approximately 1000. So this basically shows that a problem for problem database, the write QPS is almost zero, but the read QPS is approximately 1000. Or let's say, if we want to be more flexible, then let's say it can go up to 10,000 reads per second. So even for 10,000 reads per second, we can use a simple any relational database, could be MySQL or Postgres, and so that will basically scale very easily. But let's say if we want to improve it even further, then we can just what we can do is we can add a cache here, and rather than going to the problem database, we can just read from the cache directly. So this way, this scaling this part is actually easy. So you can the relational database can handle this load, but you can basically see what kind of latency you want to provide to the user. So cache is not really, I would say, absolutely necessary here, but it can optimize. One thing is that if you are going to the problem database directly, then you are making a call to S3 and then reading the file from there. So that could be latency heavy because that file will be transferred over the network. So rather than doing that, we can actually cache that file in the cache. That will also actually depend on the cache. If our cache allows us to store this kind of, this much amount of data. So I'm not really sure about Redis. Actually, I've used Couchbase, yeah, it doesn't support storing large amount of records in the cache. So I mean so so what we can do is basically we can actually push this file to CDN, and from CDN actually from CDN you can load the file directly. So user, rather than going to the problem front-end service, it can actually go to the CDN, and from CDN the file can be downloaded. So yeah, we can actually check whatever works here. So if we are able to store the text description in the cache, then we can go ahead with the cache. If not, then we go ahead with the CDN. So problem part we have scaled. Now submission database will scale. Evaluation servers, yeah. So one thing that we haven't talked about is what happens when there is a spike in the traffic. So on the problem front end, this part will work. There is no problem in that. But let's say if there is spike on the submission part, so in that case what will happen is submission front-end service is a stateless service, so that will be able to handle the load, but it will be sending a lot of submissions to the evaluation server in a very short amount of time. So if that happens, then these servers might get overloaded. So what we can do is we can introduce a queue in between. So what we will do is, and queuing technology could be anything, but yeah, for reliability I would go ahead with Kafka actually. So we don't need a super fast latency. Kafka can provide up to 10-15 milliseconds of latency if it's not applying any back pressure, it's not overloaded. So we can just use Kafka here. So submission front end service will send the submissions to Kafka. From there they are consumed by the evaluation server. uh, One more thing that is pending is basically fault tolerance. So where things can go wrong, what are the areas? So one thing is user is let's say, let's start from the beginning only. So user tries to read a problem or tries to see the list of problems. At that time, maybe I don't know, problem DB is down or problem DB is not responding or cache is not responding. In that case, user can just retry. So we can just throw an error. Problem front end service can just throw an error. User can retry. So that part is simple. Now, in case of submission, this would be a little complicated. So in submission, we have actually 3 steps. So one is create an entry in submission DB, and then send the submission to evaluations, send the submission to Kafka, and then from Kafka it basically gets consumed by the evaluation server. Then evaluation server consumes and evaluates. Then fourth step is basically evaluation marks, updates the status in submission database. Okay, so let's say if this steps fails, submission front end service is making creating an entry in submission database, and that fails. In that case, submission front end service will just return a error to the user that some issue happened, so you need to retry. Okay, now let's say one was succeeded and it fails on second. Send the submission to Kafka. This part fails. In that case, this part fails. So if that part fails, then I think it won't make sense to return the response to user and keep the user waiting. So it will be better that and sending to creating the entry in submission database and sending it to Kafka, they can be done in the same synchronous call. So yeah, what we will do is basically once both of these two steps are successful, then only we provide the response to the user that your submission is successful. If any of these fails, then we provide a error response to the user. Okay, now the third part is evaluation server is basically consumes from the Kafka and evaluates third part. Okay, so what can happen is let's say evaluation service consumed a record from the Kafka, and it's evaluating that record, and it goes down in the middle of middle of the evaluation. So what will happen in that case? So what will happen is basically let's say user will keep waiting indefinitely. So since there is no one to update the status of that submission, user will be kind of user will be stuck in sort of infinite loop. User will just infinitely keep waiting. So how do we deal with that? One thing is we can have a client timeout from the client side that so one option is we have a timer from the client end that user should wait for maybe 5 seconds only, or maximum let's say 15 seconds or 20 seconds, whatever, maybe 1 minute. That is one kind of timeout. But the client timeouts are not that reliable. So let's say what happens when user waits for 10 seconds and the timeout is 1 minute, and user closes the tab or something like that. So in that case we won't really have any deterministic state of that submission. So what we should be doing is basically on the backend side we should have some kind of timeout that updates the submission in the submission database. I mean the submission entry in the submission database, that it has timed out some kind of timeout like that. So for that what we can do is and these kind of timeouts, so basically they can be implemented by a database which basically provides a TTL capability. So what we can do is we can use Redis here, and it will have TTL for the submission records. So when the submission front-end service has created an entry in the submission database, it will also create an entry in the Redis, and that entry will have a TTL. So let's say it will have a TTL of 1 minute. What will happen is, let's say the evaluation service goes down in the middle, then once this TTL is, once this record expires after 1 minute, that TTL will basically have a side effect, and that side effect can actually go ahead and update the submission database that submission was timed out. Now implementing the side effect can be done in many ways. One approach is basically using change data capture. So I'm not sure if Redis kind of provides these kind of side effects out of the box, but I think change data capture would be, I would say, at least something that will definitely work. Change data capture. So this way we can, this part, evaluation server going down in the middle can be this can be handled. If it goes down at the third step, uh, what happens, let's say if the third step was completed and it fails at the fourth step, so evaluation service server tries to update the status in the submission database, but that fails. So in that case we can maybe retry from the evaluation server. That is one thing. Or the other thing is basically we just don't do anything. So we kind of allow it to time out, and then let the submission entry say that it was timed out. So that will also work, because these kind of things don't really happen very often. But yeah, we should first retry and then maybe allow to timeout. So what will happen when there is a peak in the traffic? So let's say if a contest is running, so in that case what will happen is users will be making a lot of submissions. They'll go to the submission front end service. Submission front end service, we will have to see that it basically scales to the peak. Cassandra should scale. Redis will also scale, and the main bottleneck here is the evaluation servers. So these are the ones who are doing the heavy lifting, and they are also taking the time. Basically, yeah, they are doing the heavy lifting, so they cannot just scale to the peak very quickly. So in that case, what will happen is the extra, the extra traffic will be basically consumed by by Kafka. So we will have to ensure in that case that Kafka is able to consume all that traffic, and from there those submissions are consumed by the evaluation server at their own speed. So yeah, so we can configure Kafka to handle that kind of load. So that part will have to ensure that that Kafka does not apply any back pressure there. I think we have covered most of the things here. Yeah. Any questions?
No.